So this is the last video dealing with valence shell electron pair repulsion theory. And in this video, I'm going to show you all of the different molecular geometries that you need to know. There's very few of them, but they're all based on those initial five. We looked at the five ones with both the electron domain geometry and molecular geometry that are the same. So we'll come across those as we proceed. But first I do want to talk to you about bond angles. Bond angles is the last piece of the puzzle in terms of getting all of the information out of what starts as a formula, becomes a Lewis structure, becomes a molecular geometry, etc. So let's start with bond angles. So bond angles, as it says, are determined by measuring from a bonded atom through the central atom and then to any other bonded atom. So this first example is really straightforward. Here's our bonded atom. We're going to go through the central atom, so that's through the one in the middle, to other bonded atom. And we would then measure a bond angle like this. So that's our bond angle. And so this bond angle is pretty simple. That's 180 degrees. And you see a 180 degree bond angle in a linear molecule. But it's not the only bond angle. There's several others, and these diagrams show some of the other ones, and we'll come across these as we proceed. The one thing I do want to point out here is to establish a bonding, and we look at repulsions. And so now that we have more bonded atoms, we bring into play more bond pair repulsions. And so what happens there when you have bond pair repulsion all around is they separate maximally. So that's why in this particular molecule all the bond angles are the same. And if we look at this molecule, because we have two different orientations of the bond, we're going to get actually different bond angles. And so we have this component in the middle. These are known as equatorial atoms. So essentially we've just taken this trigonal planar component from the top diagram and we put it here in the middle, and those are equatorial atoms. And then we have these axial atoms that go in a line, and that's our linear. So axial and equatorial, different bond angles. And as I said, we'll come across those as we keep going on. So let's get into the geometries. So I'm going to go through the first three, and then I'm going to just let you look at the final sets of geometries. But we'll go through the first three here, and they all kind of look this way. So again, we start with a steric number of 2. If you remember, the steric number tells us how many electron domains are around a bonded atom. So if there's only 2 electron domains, and those are both bonded atoms, we're going to have a linear geometry. That is just the way it is. In terms of the AXE notation, then it becomes very straightforward. AXE, remember the X referring to the ligands. If there's only 2 ligands, no lone pairs, AXE2, and the molecular geometry is linear. So this is one of those ones I was talking about earlier. This is one of those ones that gives you both an electron domain geometry and a molecular geometry that are the same. So the bond angle, as we just saw, is 180 degrees. And examples of this are beryllium chloride and carbon dioxide. If you've seen beryllium chloride before, it's one of the exceptions. Beryllium does not have any lone pairs, so it bonds 2 chlorine atoms, 2 ligands only. And carbon dioxide is not an exception, but it is kind of interesting. It does only have 2 electron domains. So this points out that even though that electron domain is a double bond, it doesn't make any difference. It's still considered a single electron domain. So there's an example of AXE or AX2 or linear molecule. And just to remind you, for your Lewis structures, as a minimum, you should be writing down the total number of valence electrons. So let's go on to the next one. So now the steric number is 3. AXE notation is AX3, and the molecule electron domain geometry is trigonal planar. So when we have all bonded atoms, the AX3 notation tells us the molecular geometry is also trigonal planar. And so that was one we saw before as well. Bond angle of 120 is from there. And so all 3 of those bond angles would be 120. So examples of this molecule are sulfur trioxide and borane, or BH3. And again, sulfur trioxide has only 3 electron domains around the central atom. One of them is a double bond, which gives us resonance, but double bond, single bond, they don't make a difference in terms of electron domains. So there is the example of a steric number of 3 and an AXE notation of AX3 to give you both your trigonal planar geometries. Well, if we take off one of those bonding atoms and add a lone pair, that's what this yellow molecule or yellow atom is showing, that's a lone pair, we change the molecular geometry. The steric number is still 3, but the notation changes to AX2E, and the fact that we have that E changes the molecular geometry. And so this is known as angular or bent. And so in terms of the bond angle, well, again, now what we have here is a lone pair with a bond pair. So that's lone pair, bond pair repulsion. And if you recall, that's a stronger force of repulsion. And so what we have here is a force of repulsion pushing that bond down, force repulsion pushing that bond down. We have bond pair pushing back, but that's not as strong a push. The force of repulsion from bond pair is less, so the net result is that these bonds get pushed down. And so a bond angle of 120 is going to change. This was 120 in trigonal planar, but it's no longer trigonal planar geometry. That lone pair makes the bond angle less than 120. So example, sulfur dioxide, an ozone, and again, here's that lone pair. So that lone pair on a Lewis structure is what's going to make this bond angle change. And so the actual bond angle that you don't necessarily see in a Lewis structure, this bond angle is going to change. It's going to be less than 120. And so here's where I'm going to let you go off on your own, and you're going to basically have a look at the different structures and come to grips with the steric number, electron domain geometry, AXE notation, molecular geometry, and bond angle. And for every one of these, there is an example given. So what I certainly recommend is pause the video when the page changes and just have a look at what's shown on the page, the different pieces of information that you do need to know and do need to come to terms with. So you might want to start pausing now. And so there they are. That's all of the different molecular geometries you need to know. And as I mentioned, all of those geometries come from those 5 starting geometries. So 5 geometries that have the same electron domain geometry and molecular geometry, that is fully bonded with ligands. And those 5 are actually shown here. They include linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And so you start with those 5 and you start pulling off atoms and adding lone pairs, and you get all of the different geometries. So that's really what you have to try to get a handle on in terms of VSEPR, shape, bond angle. It's pretty important that you spend a bit of time going through these with the examples you have from previous assignments.